Hello and welcome to Calculus 2, our first section of the semester 6.2 area between two curves. It is going to use integrals, chapter 6, 7, 8, 9, it's all integration. So before we dive into area between two curves, let's just review the area between one curve. Make sure we understand and remember the way to calculate that all the way back from Calc 1 and then ease our way into 6.2 and then push forward. So to go back to Calc 1, area under the curve, so let's go Calc 1, right, with K's. So when we have some kind of a function, some kind of a shape that we want to calculate area, so that's our f of x, x-axis, y-axis, all of the stuff we know from before. What we said is that we can come up with a representative rectangle which will have delta x as its width, and the height of this rectangle will be given by f of some xi, which is a value. So you have delta x, which is the width, and f of xi at whatever the location as the height, and when you multiply those two numbers, you get the area of this, what we call representative rectangle, delta x. So to find the area of a single rectangle, I will write f of xi times delta x. And that is 1. So area of one rectangle. Now I am going to compute every single one of these rectangles between, let's say, A and B, which will add a lot. So I starts at the first rectangle and goes to some number of n rectangles. Maybe you have 10 rectangles, maybe you have 10,000 if you are programming, and you should. Maybe you have 1,000,000 rectangles. The more rectangles you have, the better the approximation. So this with the sum will be area of many rectangles. Now, to get the exact area under the curve, we need to use infinitely many rectangles. Because when you use infinitely many rectangles, the delta x shrinks to 0, and there is no more width for the rectangle, which eliminates the error. Let me draw a larger picture here. Say that your representative rectangle is this fat, and you have this curve on top. So if I make a left rectangle like this, then error is right here. If I make a right rectangle, then error is right there. So no matter whether I use left or right rectangles, I always have error either below or above the curve, because there is the width to the rectangle. But if I introduce infinitely many rectangles crammed into a finite length of A to B, then the width of each rectangle will be 0, in which case there is no width for the rectangle and you can't make an error, which means you can get exact when you introduce a limit with the number of rectangles going to infinity, and now this will be exact area with the limit. So it builds up little by little. And this is what you guys learned in 5.1 and 5.2 in your Calculus 1. and you know this as a Riemann sum area under the curve, and it was denoted by the definite integral between a and b f of x dx. So this definition was there, and now I have it here broken into pieces. So we see area of one rectangle, which is just height times the width, and then we add a whole bunch of them. So that's, you add maybe another 10 or 15 or whatever, and then you say, I don't want 15. Instead of putting 15 here, I'll put n, and then shoot that n to infinity to say I'm going to have infinitely many rectangles. As soon as you have infinitely many rectangles, you lose the error because of the width, right? You lose the error, and it becomes the exact area under the curve. So now, to calculate area under f of x, all we need to do is to say a equals integral, well, f of x on interval ab, right? I have to put that. So to calculate area, exact area, you need to calculate the integral, the definite integral a to b of f of x dx. Now we also need to make sure that f of x needs to be, well, let me put it here, f of x needs to be positive or equal to 0. So this is a condition for the calculation. That function has to be above x-axis. What happens is if the function dips below x-axis, it creates negative area and then the net area, and it messes up the actual calculation. The best example to learn that with is the sine x. We'll get there. So just to review real quick, if you want to calculate area under the curve, and that curve is just a straight line like this, creating a to b, which is 0 to 1, 2, 3, 4, 5 in this case, with a height 2, we all know that this is a rectangle. 5 times 2 equals 10. Are we all bueno on that? We should be, right? I understand it's been 20 years since you learned it, but right, leave it there. So we know that area is 5 times 2 equals to 10. But we also can use the integral to calculate this, because area is integral 0 to 5, because those are your a and b limits on the x-axis. And then we have our function, which is a straight linear constant line of y equals to 2, f of x equals to 2, so it's just 2 dx. Integral of 2 dx is 2x, computed from 0 to 5. We get 10 minus 0 equals 10, and we have the same answer, right? So we are able to calculate area of the rectangle using the formula you learned in second grade, or using the formula for integration that you learned in, 13th grade or whatever it is, right? Now, it is important to note that this function y equals to 2, constant function, is always above x-axis, never dips below on the interval a to b, and therefore, right, we all have, all we have is the positive area. Now, if you observe the sine function goes above from 0 to pi, and then below 0 to 2 pi. And if you use the same method to calculate area under the sine, it's not going to work. If you say that area is equal 0 to 2 pi of sine x dx, you will calculate 0. But you know it's not 0 because you can color, right? I can color this, so there is area. So we have to fix that. So here is the calculation, right? Negative cosine x from 0 to 2 pi, and then you go negative cosine 2 pi plus cosine of 0 negative 1 plus 1 equal to 0, and you say, nope. So why is it wrong? It's wrong because there is a positive area calculated here, negative area calculated there, and when they add together, you get the sum net area of 0. But you don't want that, right? You actually want to know the area of what you can color. So you have to be smart and break your picture into two parts and apply absolute value on the portion of the graph that dips below x-axis. So that was the trick we used last semester to figure out area under the curve. So the sine function now, this is the positive area, this is the negative area. So we are going to take this piece and bump it up right here, and it will become a positive area, and then we will be able to compute that. So now, how do you get this? Well, you will use the integral 0 to pi of sine x dx for the first one, plus the absolute value of the integral pi to 2 pi sine x dx for the second one. And that's how in Calc 1 you fixed your negative areas. Now, this could be x cubed, it could be any other function that dips below x-axis, it's okay. You just put the piece that is below x-axis, you put that piece into absolute value to make the value positive. So now, when I integrate this mess, I get negative cosine x from 0 to pi plus absolute value of negative cosine x from pi to 2 pi, and then we go from there. So negative cosine pi plus cosine 0 plus absolute value of negative cosine 2 pi plus cosine no coughing of pi. So now, cosine of pi is negative 1. So we have negative 1 plus cosine of 0 is 1 plus absolute value. Cosine of 2 pi is 1, so that's going to be negative 1 plus cosine of pi is negative 1. That's 1 plus absolute value of negative 2, which is 2 plus 2, which is 4. So now we know that area under the sine graph is 4. If this graph was done in, I don't know, feet, it will be 4 square feet of area to paint. Now, clearly, we don't care about the actual area. We care about this calculation when we want to calculate the energy of the system, because energy of the system in physics is going to be area under the curve. There are many concepts in physics which will be calculated by area of the curve. If anyone has to take circuits, you will see the integrals, and that is also going to use integration to calculate concepts in there. So we now understand that we can calculate area under any shape function, and we just need to be careful if it dips below x-axis to chop off that piece, put in absolute value, and just add all of that area together. However, if we just have function above x-axis at all times, which is the first example there, then you just do the straight integration and you are done. So you have to know graphing, right? You have to know if the graph goes below x-axis. So that was the review from Calc 1, and now we finally are hitting our 6.2 area between two curves. What two curves? Curve f of x and curve g of x that are one on top of the other. They're creating a shape in between. So one of my project problems. Some of you are familiar that my courses have projects. No one else does, but you still keep signing up, so amazing. Yes, I'm the only one. Oh, if you just knew that earlier, right? No. Okay, so I will give you one of the past project questions. Project questions are something applied that you get to measure, play with, and so on, and then crack the math about it, right? So my one of the problems that is in the pool that I sometimes pull out a hat and slam it on the project sheet is to calculate the area of the Nike symbol. That's all I give you. I don't give you anything else. That's it. The full statement of the problem. Calculate the area of the Nike symbol. And I'm done. Now, what you are going to do, you are going to print the Nike symbol off of the internet. You are going to trace Nike symbol off of your shoe if you have it, right? Or if you hate Nike, you are going to find the anti-Nike poster and then trace the Nike symbol off of the anti-Nike poster, right? You are going to fall into one of those categories, right? And once you have that symbol on the piece of paper, then you use grid paper to figure out what are the two functions that create that symbol, right? So let's say symbol looks like this, right? So these might be two parabolas, right? Two parabolas that intersect, and you need to fit and figure out what those lines are. Excel can do that for you. You just use the square paper and figure out what these points are along the way. You stuff that into Excel. It spits out the functions. And now you have two functions, f of x and g of x. And now it's time to use today's lecture to see how to calculate the area of the symbol like this, or whatever else you can come up with, right? So let's say you have a t-shirt design and then you put some kind of symbol like that, right? It's like some evil smiley face or whatever it is, right? So now you just want to know how much paint goes into making this, right? So what's the area? So what do I have? I have a linear line and I have a parabola underneath, right? So it's your job as engineers to figure out what functions you have. Is it a linear equation fit, which is a straight line? Is it any kind of other polynomial? Is it exponential? Is it logarithmic? Is it trigonometric? Is it a square root, cube root, right? You as engineers have to figure these things out, and then you are going to pick the points off and use the appropriate function form to come up, right? That's already application at the end. And once you have f and g, we're going to crank the lecture now and see how to compute the area. So area, right? And you will find that all around you. You can always ask and look for what's the area between two curves. So now let's take a look at the theory and what we need to do. So we're going to do obviously just a general drawing in mathematics, x, y, and we're going to have two arbitrary functions, intersecting somewhere. Make sure you are not intersecting them on the y-axis so it's easier to see. Now, drop these verticals down. That's where your A is. And drop the other vertical down. That's where your B is. The top function I'm going to call f of x. The bottom function I'm going to call g of x. Clearly, I am interested in the area between two curves, so that's that football-like shape in the middle. We all following that? So this is what I am interested in right here. Now, how do we get this? Look at this. We are going to calculate area from A to B under f of x. That is going to give you everything all the way down to the x-axis. Does anyone see the next step? Excellent. Calculate the area A to B from g of x, which will be the stuff we don't need. And by subtracting the two, we have exactly what we need. Does it make sense? So, the area is equal to blue minus orange. So what is the formula? The formula is, here, I'll write it in blood. A equals integral A to B of f of x minus g of x dx. Make sure you put these parentheses. They're not there for decoration. We need them. Does this formula make sense? Okay. Are you all familiar with the meme that has a couple of those brains that are lit at a different level? Are you all familiar with those types of memes? Do I need to pull one up? Let's not waste time. So, this is the way we're going to learn pretty much all of our formulas in Calc 2. It will be the levels of how much the brain is lit, okay? The least amount of brain lit is memorizing f minus g. That's the least amount of brain being lit, okay? Because if I switch f and g into anything else, immediately lost, right? So that's the least amount. But you still at least have some lit part to there, right? What's the next level of lit? Remembering top minus bottom. Because do you see that in this part of the picture, G is on top and F is on the bottom? Right? So it's not always that F is on the top. Right? So we cannot remember F minus G. We can, but it's not going to work all the time. We are not remembering F minus G, because F and G could swap places. And you already see that they did swap places as soon as they passed B. So what's the next level of lit brain in the meme? It's remembering formula as top minus bottom. That's still not the best way, but it's much better than F minus G. So I can just say over here, top minus bottom. But again, we are not at the highest cognitive level, right? So what is that lit brain that takes all the whole picture, right? It is remembering it as far minus close. That's the one that I want you to remember. Far minus close. And I'll explain. So I'm changing this top minus bottom. I don't care about it. Into far minus close. Now, what do I mean by far minus close? Look how powerful that concept is. If I have two graphs and I have f on top and g on the bottom, when you start measuring from the x-axis, here is your far and here is your close. And you'll say, yeah, nothing new, I know that, that's called cool. Sure. Now I'm going to present you with a dy integral. If I draw a dy integral, which is something you did not deal with in Calc 1. You never had dy integrals in Calc 1. Everything was f of x. Now you have f of y as well. And when I put two functions, say I put a square root of x and I put a linear line like this, and I want that to be sideways as a dy, which one is on top? You see that you can do top minus bottom now? It's far minus close. They switch the role. If you want to calculate this one in respect to x, then the root is far and the linear is close. So I'm going to now do the other side. Close and far. Do we see they're flipped? So that's what I hope you will remember. Far minus close. Not f and g, not top and bottom, not right and left, but far minus close. That's all I care about. Far minus close. Now, obviously, when I have a dy integral, that prompts me to write the y version of the integral, which is integral c to d of f of y minus g of y dy. And that would again be far minus close. We are remembering, but this is in the y direction. Now, most of the formulas that we will learn in chapter 6 will have its x integral and its y integral as well. Time for some numbers. Let's calculate area between square root of x and x on 0 to 1. Right? That's what we want to do. We are going to graph we have our 0, we have our 1, 1 over here, and we are looking for the area in between. So I want to set up my delta x integral, which means that I am going to use f of x is on top, which is the far one, and that we see it's a square root. So integral 0 to 1 of the square root of x minus g of x will be on the bottom, which is the close, that's x, equals, and now we just compute. So what do I have? Ooh, I forgot to write dx. Holy nightmare. There we go. What is the integral of square root of x? Very good. And what is the integral of x?
Divided by 2.
Divided by 2. Oops. From 0 to 1. Area is going to be 2/3 minus 1/2, and then minus 0, which is common denominator of 6, 4 minus 3, 1/6. Is that any good? Good, thank you. It's like, yeah, say it's good. It's just, the sooner we finish, the sooner we're done. All right, cool. Well, we're going to also hopefully get 1/6 if we use dy integral. So area equals 0 to 1 again, because it's also on the y-axis is 0 to 1. It's a bad example, obviously. Now, when I'm looking from the y, do we all see that the linear line is the one that is far? So what do I have here? The linear line, I have two functions, guys. I have a function y equals square root of x and a function y equals x, right? We have two functions. When I'm looking in terms of y, my entire integral must be in terms of a y. So what's my function that it's the one that it's far, the one that goes there? It's just y, because y equals x, x equals y. Minus, and what's the other one? Y squared. You have to solve these functions for x, because when you are doing the integral in terms of x, your function is f of x. When you're doing the integral in terms of y, your function is f of y. X equals f of y. So when you flip this one, you will have x is y squared, and when you flip this one, you just get x is y. So it's pretty much the same. So now we solve this integral, and we better get 1/6, otherwise we break mathematics, we can all go home. What is the integral of y? Okay, and what is the integral of y squared? Excellent. 0 to 1. So now we get 1/2 minus 1/3, which is 1/6. Woohoo. Now, before you attack me, why do we bother with dy integral in blue if the dx integral in black worked just fine? There are certain problems that cannot be solved using dx. And there are certain integrals that cannot be solved using the blue. And there are certain integrals that can be solved using either of them, like this one. Okay? It doesn't matter. See? Excellent question. It doesn't matter where the stuff is. It's always going to be far minus close. You put them on the left, one is going to be far, one is going to be close. You put them underneath, one is far, one is close. That's the way this works. Now, if one is below and one is above, then you can do either way you want. let's do more. I mean, we're going to do a lot of examples. This is it. There's nothing else in this lecture. You're learning this one formula in x and a y form, right? We just need to do a whole bunch of examples until it makes perfect sense. Before we go dig into a little bit spicier examples, let's have you guys figure out one of these. So how about area between y equals 8 minus x squared and y equals half x plus 2. If you are having issues with graphs, you should not have issues with these two graphs, but if you do, computers in your desk have access to Desmos. Plug both of those functions on two different lines, right? And see what the graph looks like. One is the parabola opening downward because negative x squared. The other one is a linear line, and they are going to intersect, right, and create that shape. You can also use Desmos on your cell phone if you are lazy to log into the computers or install a graphing app, free graphing app on your cell phone, and use it. You will not get far without graphs in the first couple of sections of this course. You will also need to know those graphs for your exam. No graphing calculators. And you need to know the graphs because top minus bottom, far minus close, right? So you need to know which one is on top, which one's on the bottom. Or just the website on the phone? They have the app for the phone? Just trying to figure out how long before they start charging. They're all good, right? Free. Everyone gets some more. Okay, $3 now. You say, $3 times $3 times 3. That's going to go. What is the issue that you should already have with this problem? You already know what's on top, what's on the bottom, right? You started writing the integral. What's the issue? Limits A and B, very good, right? So what are you going to do for the limits? They don't intersect at the x. X-intercept means function cuts through x-axis. They do not do what?
Each function is equal to each other.
Beautiful. Equal the two functions to each other and solve algebra equations. So you see how each function is y equals? Set the two functions equal to each other, move all the stuff on a pile on one side, and you will have a quadratic equation that you have to solve, and that will spit out two x values. Smaller one is your A, larger one is your B. Now you're probably going to have disgusting numbers because I just do this. But it can be done. It would be funny if the answers are like 2 and 7. Because I computed everything against Okay. So if we get at least something nice, or it's the square root of 35. All right, let's take a look at this together. The way I graph this, because I really don't care about the gory detail. What I know is that my y-intercept on the parabola is 8, because when x is 0, right, for y-intercept, y is 8. So 1, 2, 3, 4, 5, 6, 7, 8. And then I'm just going to drop parabola down. I don't know where it exactly cuts through x-axis. I don't care, right? I just want to know the shape as close as possible. Then I have the linear line with a y-intercept of 2, and it has a positive slope, so it's going to go something like this. I don't really need a greatest precision for any of this stuff. This is good enough. What I see on the picture is that if I am using dx, that this is far and this is close. So when I set up my integral, it will be the quadratic function minus linear function in parentheses. Now I need my limits a and b, and the limits a and b are where the intersection of the graphs are. That means I have to set these two equations equal to each other. Now the first order of business is to put everything on the same side. So I'm just going to say x squared plus 1/2 x, and then minus 6 equal to 0. I move everything to the right. X squared becomes positive, 8 becomes negative 8, and then plus 2 is negative 6. And then I'm going to multiply the whole thing by 2 to kill the fraction. And this is something that I need to solve. Now, you can use quadratic equation. You can use factoring, guess and check method, essential oils, I don't know. Whatever works, just get the right solution, right? We have negative b plus minus b squared minus 4ac. Is that really 48, a 49, and a 7? Is it? Is this negative 1 plus minus 7 divided by 4? To get negative 2 as one solution, and positive 3/2. Is it? Did anyone compute this?
I did it. Like I got negative 1.9 and 2.9. But I kind of did it a little bit differently. Like I didn't take away the fractions on my side, so.
When in doubt, ask Mr. Wolfram. This is another tool you can use. You talk to it, and it gives you the answer. Solve 8 minus x squared equals 0.5x plus 2. Where did I make a mistake?
That's similar to
Oh, 4a, c, a is 2. I went 2 times 2 times 12, and it's 4 times 2 times 12. This is 96. And that makes it a square root of 97. Okay. Approximate numbers. Negative 2.7 and positive 2.2. Negative 2.7 and positive 2.2. Cool. I have my integral from negative 2.7 to 2.2, and then I have the parabola 8 minus x squared minus 1/2 x plus 2, and then dx. Integrate. Well, we can first get the like terms and so what do I have? I have negative x squared minus 1/2 x and then plus 6 dx. Integrate minus x cubed, no coughing, over 3 minus x, easy, x squared over 4 plus 6x when we integrate each one of the polynomials. And now we just plug in the values and we get a number. 2.2 cubed, or negative, over 3 minus 2.2 squared over 4 plus 6 times 2.2 minus negative 2.7 cubed over 3 minus, it all goes in parentheses, negative 2.7 squared over 4 plus 6 times negative 2. I just regretted this. Equals a number, huh? Is that good enough? Because you know that your homework is going to be 1 and 17 and things like that, right? And your exam too. So ugly calculation, but we don't care about calculation there. We care about setting it up, understanding the concept. So my area is here. I will go far to reach, I will go far from the x-axis because I'm doing the dx integral. I will go far to reach the parabola minus close to reach the linear line. Far minus close will give you the stuff in between. And then you integrate using 5.2 from Calc 1. All right, let's pick a problem from the textbook, the one that is going to have what you would call nice numbers, because these are apparently not nice. Homework exercise 20. It has a graph with couple of functions. It has a line like this. It says x equals y over 4. It has a line like this, it says y equals to 4. It has a line like this, and it says x equals square root of y. What is the area inside? You are not discussing the problem with the people sitting next to you. You already decided dx or dy or no? I heard dy. All right, let's see. All right, let's take a look at this together. I cannot use, well, I can, but I don't want to, dx, because I would have to use multiple integrals. If I try to use dx and draw the vertical representative dx rectangle, you can see that the top of that rectangle would ride the black function first and then the green one, which means two different integrals. You would have to have integral that goes from black to red and then from green to red. Two integrals, which is manageable, but let's check dy and see if we can have one integral only. So if I draw dy, which is the horizontal representative rectangle, as this rectangle slides from the bottom all the way to the green top, the green line to the top, you see that it always rides black and red functions only, which means single integral. Anytime when any of the extreme points of the rectangle has to hop a function from one to another, you are introducing another integral. So dx is going to be first between the black and red, and then dx will be between green and red. So that's two different combinations. That means two integrals. The horizontal one, dy, only rides between black on a close and red on a far, which means a single integral. So I'm going to use dy because dy is going to give me one integral only, and I'm lazy, so I just want to do that one. As I am setting up a dy integral, I am using y limits, which means 0 to 4, because the lowest level that the black rectangle is going to be at, the dy, is going to be at 0, and the highest level at which the black rectangle is going to be at is the green line, y equals to 4. For dy integrals, use y limits. For dx integrals, use x limits. Maybe you need to write that down. For dy integrals, use y limits. For dx integrals, use x limits. Since this is a dy integral, I am going to use y limits, therefore 0 to 4. Now I need far minus close. In this case, it's going to be red minus black, because y-axis, right, I'm doing the dy integral, so y-axis is where I'm measuring from. Red is further away than black. So red minus black, that means root y minus y over 4. In parentheses, dy. Integral of square root of y is good old y 3/2 over 3, and then you put a 2 on top, minus y squared over 8, and then we have our limits 0 to 4. Now we have 2/3, 4 to the 3/2, minus 4 squared, 16 over 8. 2/3 times, and now we have to calculate 4 to 3/2. Half is a square root. Square root of 4 is 2. 2 cubed is 8. So this is 8. Minus 16 divided by 8 is 2. So 16/3 minus 6/3 is 10/3. So hope is that the answer is 10/3 on this one. Now, let's say that you just spent 15-20 minutes figuring out this integral because your skills from Calc 1 are not there yet to be able to do this in under 2 minutes, where you should be, right? You struggled, you are learning or relearning or reviewing, so on. You are sitting at home, working on homework, you have no clue if it's correct. What do? You ask Mr. Wolfram to verify this answer by plugging in your problem into the here, right? And you do that by talking to it. The way you would communicate problem to me or your friend is the way you communicate that problem to the software. You say, integrate, and then you type in your problem. That would be, you can use y if you want. Y raised to the 0.5, that's a square root, right? Because square root of x is x to the 1/2. 1/2 is 0.5. So y to the 0.5 minus y divided by 4. You close the parenthesis, and then you just say from 0 to 4. This is the way you would read the problem out loud to someone. That's the way you type it in a program. You push enter, and you hope for 10/3. Boss, right? If you pay at the website, you can click step-by-step solution, and it will give you if you pay, right? For the software. Now, I think that this software is one-time purchase for the app, for cell phones and tablets, and if you are purchasing it on the website, it charges you every month. So if you are really struggling with integration, if you need to see the steps for every integral you will ever do, purchasing a $4 or $5 app for the tablet might be something that you could see as a value. Obviously, you can always bring the problems to my office hours. We'll go step by step for every single one you need. But if you want to work on these problems at 3 a.m., right, and you obviously don't want to disturb me at 3 a.m. because I'm playing video games, right, that's where I'm dangerous, then you can use the app, right, to check the steps. Make sense? Cool. Yes.
I think integral calculator, like if you Google that, it'll like show you step by step for free.
Oh, for free?
Yeah.
Perfect.
What was that?
What was the name?
Like I just Googled.
What was the name of the software program? Website?
Website.
Yeah, website.
Integral-calculator.com.
Integral-calculator.com. Apparently free one.
There's also one the same
There it is. So it looks like you stick your problem right there, and you push go, and you can see the steps, right? So let's test this. Hold on. I got this. Square root of y minus y over 4. Then we change this over here to a y. I should have done it in X, but you know, such is life. And then I guess you poke here, you press 0. You poke here, you press 4. And you say go. Nice.
Yeah, click that show steps button and it'll break it out.
I would have to work really hard to have this many steps, but that's okay. Wow. Amazing.
If you highlight some of them, I think it goes over like what rule is being used for it.
Wow. At this point, I want the whole classroom to pause and realize that someone coded this bot. and said, hey, it's just gonna make it free.
Thank you.
Yeah, right? And it's going to work for 100 problems. It's gonna fail you once, and you're just gonna call it crap. This is the society we live in. Right? I know. Just be amazed that exists. Awesome, cool. So you can use this integral calculator, integral-calculator.com. You can use Wolfram Alpha if you just want the answer. It's real quick, right? You don't have to poke and think. You can like type in and like talk to it. That's why I like just to verify the answers, but it looks like it works. And then you have your Desmos for quick, easy, beautiful graphs, right? So you can use all of those tools to help you go through this and keep checking your answers at all times. Cool. We're not done. But wait, there's more. If you call in the next 2 minutes, I'm going to throw in a problem that is going to look like this. Area between x equals y cubed minus 4y squared plus 3y and x equals y no coughing squared minus y. Sure, free of charge. I mean, you dished out $600 for me to switch it, but there's no charge right now. The charge already occurred. $2,500.
Big discounts.
We did not have a problem like this yet. I did talk about this, but we didn't have a problem like this yet. Let's go, Desmos. You have to grab this and try to figure out what the hell is going on.
You actually know what this is. It's crazy. I mean, is that a 17? Yeah, I even take it to like basic horizon. Yeah. Right.
I mean, I was looking at it before. I was like, I saw the one plus like time logo. I was just like,
When you use Desmos now, please type it as x equals. You cannot do just the y thingies because it's trying to grab. So x equals, and then on the next line, again, x equals. The second you saw it, right? You knew it was going to have the addition.
It's not a function.
Great. In terms of x, it's not a function. In terms of y, it is. Which is why we have dy.
That was shaky hands right
He's
going 0 to 1. That's the function.
0, 1, then 4.
Yeah. 0, 1, then 4.
Yeah.
Because
Also, it's 2.
I got 4 equals 2. Do it like this. Got like 0, 1, 4. That's how I did it.
Oh yeah, no, yeah, I was in the middle of doing that. Yeah.
Oh, but I don't know which one. I don't know which one. You know which one, like the.
maybe closer. Because now I'm assuming it's from 0 from 0 to 1 is like this, and then 4 is way here.
Yeah, right, 0, 1, 4.
Yeah. I only had it for maybe a few months because it was on sale, but then you could also get
Okay,
student
let's
discount.
talk. Let's figure some stuff out. If you use the tech to graph this and you zoomed out enough to see, you will see 3 intersections creating 2 areas between curves, and you see that it switches which one is on top and which one is far away, which one is close, right? So if I am to attempt and graph this monstrosity, I'm going to start by graphing the parabola first, and then I'm going to snake through the cubic function. And what they do is they intersect far out one more time. So now I have 2 areas to worry about, and you see that for one is going to be f minus g, and for the other one is going to be g minus f, right? So we're going to have to set them up that way. And we are going to have the bottom list over here to be 0, bottom limit. Then the middle limit over here is 1. And we still have this limit here, which is going to have some unknown value on the y-axis. We need to figure out that value. We don't know what it is. This is where we are going to use pre-Calculus 1 methods from chapter 2, section 4. Okay, we don't have to be that particular. So there are ways in which you can determine what that number is. We are going to, as usual, we are going to set these 2 equations equal to each other, which means I'm going to have y cubed minus 4y squared plus 3y equal to y squared minus y, and then put everything on a pile, which is y cubed minus 5y squared plus 4y equal to 0. Now, when you factor out y, you get y squared minus 5y plus 4. And you already have that solution y equals 0. You already knew that solution, but there it is. And now you have the quadratic to deal with. And that quadratic now you can just factor into y. Very good. And y. Nice. So the unknown value is y equals to 4. It also gives you y equals to 1, which we already knew from the graph. So they intersect at 0, they intersect at 1, and they intersect at 4. We are setting dy integrals. And then we're done. Okay. Integral 0 to 1. And we're going to do black minus red. You can say right minus left, right? So 0 to 1, black minus red. Black is the cubic. So we have y cubed. What is the y cubed? Minus 4y squared plus 3y minus the quadratic, which is y squared minus y. So y squared minus y minus the cubic, y cubed minus 4y squared plus 3y, close the parenthesis, dy. In this case, we must have two integrals because there are two separate areas to compute, and the line which goes to the left or right or top or bottom switched on you at the point of intersection. I'm going to jump again to the picture and then we'll be back to calculating this. I'm going to show again on the picture that between 0 and 1, black is on the right. And then between 1 and 4, you see that it goes cubic minus quadratic. And then when they switch on the picture, you have quadratic minus cubic.
So that plus there, are you adding them together? Or are you going to add the...
Yes, because the 0 to 1 is the area of the small football, and then you need the area of the big piece on top. You're looking for area between two curves, right? So you separate, you're integrating separately. You have to add them together for the total area of everything. And from now, it's just the grind work to get the number. We simplify this into y cubed minus 5y squared plus 4y dy, and then plus integral 1 to 4 of, if you want it in order, negative y cubed positive 5y squared negative 4y dy. Integrate everything. Y to the 4 over 4 minus 5y cubed over 3 plus y squared over 2 when they cancel. 0 to 1 plus negative y the 4 over 4 plus 5y cubed over 3 minus, I did this wrong, right? This is supposed to be 2y squared. Minus 2y squared from 1 to 4. Plug in 1. We get a quarter minus 5 thirds plus 2. Plug in 0, everything dies. Plus, open parenthesis. Plug in 4, that's 4 to the 4, but 1 4 will cancel, so it's negative 4 cubed. That's a 64. Plus 5/3 times 64 minus 32. So that's when you plug in 4, and then we are supposed to plug in 1. Minus, it will be actually a plus 1/4, and then in plug in 1, that's minus 5/3, and plug in 1, and the minus of plus 2. 1/4 minus 5/3 plus 2 minus 64 plus 5/3 times 64 minus 32 plus 1/4 minus 5/3 plus 2. Okay, so is there anything I can cancel? Great. We can deal with this. Then 8 over 3 minus 32. Now 1/4 and 1/4 is a half. Minus 5/3 minus 10/3 plus 4 minus 32. Okay, let's see what else we can get. Is there anything else that it's okay? So these two are already common denominators, so I have 1/2 minus 28 plus 118 over 3. That's still not divisible. Common denominator of 6. That's a 3 minus times 6, right? Yeah, 28 times 6. So what do we have? We have 120 plus 48, so that's 168. And then plus double this, 236. Let's say all of this is good, okay? So we have 239 minus 168 divided by 6. When you subtract, 23 minus 16 is 7, so 71 over 6. Perfect. That's it. Walk away. We got a number. Next time you're tutoring someone and they tell you that algebra problem is long, start flipping your notebook, right?
So that number just represents the area of both of those.
Of both of these, yes. That's how much square feet, square meters, square inches you have to paint with the right. So that's the coverage. Most of the paint says how much it can cover on a can, right?
So you wouldn't be really interested in figuring out that separately. You just want the total area so you could do whatever you need to do.
Well, we did figure it out separately because we had this integral here was 0 to 1, which corresponds to this little
and then you just add
piece,
them together.
and then we add the other one in. Yes. So we did figure them out separately, and that's why we have the plus in between to say the small area plus the big area is a total area of both of these. You have it for one more? It's not an option. One more, right? Because this is going to be one of your favorites. Let's see.
I just want actually figure it
All right. The last problem to practice for 6-2, well, they take the break, is, let's do something civil. Here, problem 28, area between y equals sine x and y equal sine 2x. They have a couple of trig ones that you can enjoy. Oh, by the way, when the textbook has a little picture with a blue T next to it, that means you have to use technology to integrate because you don't know integration techniques yet. We learn integration techniques in chapter 8. We are currently in chapter 6. So anytime you are solving a problem on MyMathLab or the homework in the book, if it has the blue T in front of the number, you will have to use software because you don't know integration by parts, you don't know trig sum, you don't know partial fraction decomposition, and so on. So you can't integrate. Yeah. Oh, the interval will be the first, yeah. Thank you. Do we do 1 or 2? 0 to pi. Excellent. 0 to pi. Have a little bit of a trigonometric equation this time. Brush up one.
Yeah.
It's real time, right?
No, I'd be fluttering a lot of us.
Much better than the linear function.
So it's going to be 2 parts again. This time is it very reflected?
Yeah.
So we don't need to get into it. Oh, we kind of
Yeah, we know that is.
Sine 2x equals 2 sine x cosine x.
it goes below the x-axis? So do we have to use the absolute value for the whole thing? What do you?
No, that when over here also, if you take we only use that for a single function. When you have two,
Okay.
because the difference between, right?
Okay, yeah.
The difference between is always the
Sine
same.
2x equals
Okay, yeah.
sine x
All right, thank
equals
you.
sine x. Then I put like, you can sine x, you can divide cosine x. Or cosine squared x. Oh, cosine. Or sine squared x over cosine.
Let's take a look at this problem together and then go to a break. So area between two curves. I need to graph this in front of x in sine and cosine function. Speed up the oscillations. It's also called angular velocity and a whole bunch of stuff. So if you draw, we know that sine, so this over here is just your sine x 0 to pi. And we'll call that sine x, right? Now, sine 2x is going to be twice as fast, which means it's just the wavelength and how fast it moves. Which is why some of you have probably seen my shirt. It's a red shirt, but the writing says this shirt is blue if you run fast enough. It's actually a joke. That includes that number 2 in front of x there. So there's going to be a half over here, pi over 2, and the sine 2x is going to make a full oscillation, which means goes up and down and ends at full oscillation, ends at pi. So it's going to go up and down and up again and end up at pi. We see that the function intersects, right? These two functions intersect at 3 locations. They intersect at 0, they intersect at this unknown location, and they intersect at pi as well. To find the unknown intersection, we are going to set two functions equal. So sine x equals to sine 2x. This is where your knowledge of basic trig identities kicks in, because sine 2x is equal to 2 sine x cosine x. And then we bring all of the trig on one side and factor. Do not cancel. You cannot divide both sides by sine x to cancel it, because sine x can be 0. And in that case, you are dividing by 0. That's not allowed, right? That's why you cannot cancel sine on both sides. You have to bring the sine, this is equal. You have to bring the sine to cosine x minus 1 in parentheses when you rip sine out of each of the terms, right? You rip the sine out, and you're left with 2 cosine, and then when you take the sine out, 1 stays there, so minus 1 equal to 0. Sine is 0 at 0, pi, 2 pi, 3 pi, 4 pi, right? Every pi gives you 0 for sine. Now you also have the other equation that you have to solve, and that's 2 cosine x minus 1 equals 0, which is 2 cosine x equals to 1, which is cosine x equals to 1/2. Now, when is the cosine 1/2? Yes? Pi over 3. Very good. X equals pi over 3, because cosine of pi over 3, cosine of 60 degrees, is 1/2. Now, there should be another value, right, 2 pi over 3, but that's going to be outside of our interval, so we don't care about 2 pi over 3 value. Every time you solve trigonometric equation, you are going to have 2, 3, 4, 8 solutions, blah, 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 right? So basic sine and cosine equations should return 2 solutions. We see the 2 solutions on the side, the one that we care about. So we don't include that one. I said 2 pi over 3, that's wrong. It's 5 pi over 3, I'm sorry. Cosine is positive in the fourth quadrant. Well, don't need it anyway. Cool, we found out that the mystery intersection is at pi over 3. Right? That's our mystery number. Pi over 3. So now I have far minus close. So the first integral is 0 to pi over 3. The top function is sine 2x, and the close bottom function is sine x dx. So that's the first piece. Let's do blue shade on it. So that's the blue one. Plus integral pi over 3 to pi, and now you see that sine x is on the top and sine 2x is on the bottom. So sine x is on the top, sine 2x is on the bottom. We can hit this with orange, and that gets the orange star as you review these lectures later. All we need to do now is integrate, stick some numbers in, and we're done. Integral of sine 2x is negative cosine 2x over 2. Very good. Minus integral of sine is negative cosine. From 0 to pi over 3, plus, and now we have the same players, just in the different order. So we have negative cosine x minus negative cosine 2x over 2 from pi over 3 to pi. Can we ignore 0 like we always did? No. Cosine of 0 is 1. We cannot ignore it. Negative 1/2 cosine of 2 pi over 3, right? Plus cosine of pi over 3 plus cosine 0. Now we have the big fat plus for the second calculation. Negative cosine pi plus plus 1/2 cosine 2 pi minus, open parenthesis, negative cosine pi over 3 plus 1/2 cosine 2 pi over 3. Lock the doors. No one is living. Cosine of 2 pi over 3 is negative 1/2, right? Whatever I say. All students take calculus. This is where the positive quadrants are. If I have cosine of 2 pi over 3, that sits in the second quadrant. Cosine is negative in a second quadrant because all positive, cosine positive. That's what A and C stand for, right? All meaning sine, cosine, tangent. So, cosine values are positive in first and the fourth quadrant. Since I have cosine of 2 pi over 3, and I know that pi over 3 for cosine is 1/2, so negative 1/2. I have negative 1/2 times negative 1/2 plus cosine of pi over 3 is 1/2 minus, open parenthesis, cosine of 0 is 1, so I have negative 1/2 plus cosine of 0 is 1. Big fat plus. Cosine of pi is negative 1, and you have a negative in front of cosine, so stick that negative in there. Plus 1/2 of cosine of 2 pi is cosine of 2 pi 1. Cosine is the one that starts at y value 1, dips below, and at 2 pi ends up, right, at 1 again. So cosine of 2 pi is 1 as a y value. What else do I have? So I'm done with this, I'm done with this. So now we're going here, minus cosine of pi over 3 is 1/2 plus 1/2, and then this is negative 1/2. We already discussed cosine of cosine of 2 pi over 3. All right, fix this. We have a quarter plus 1/2 minus 1 minus 1/2 is 1/2. So these guys are going to cancel. Big fat plus. Here I have 1 plus 1/2 plus another 1/2 and then plus a quarter, because this over here is negative quarter, and then the negative in front gives you a positive quarter. Welcome to Calc 2. Let's take a break.